The solar system is a vast system of astronomical bodies that formed approximately 4.5 billion years ago. It is the gravitationally bound system of the Sun and the objects that orbit it, either directly or indirectly. Of the objects that orbit the Sun directly, the largest are the 8 planets, with the remainder being the smaller objects, the dwarf planets, and small solar system bodies. Having a diameter of almost 300 billion kilometers, it is enormous. But what if we could fit it on Earth? Or even better, fit it in a small patch of grass in my backyard using just these items. In this video, I will make a scale model of our celestial solar system. To give you a better idea, this is the area where I will make the model. Not too big, not too small. Because it is a scale model, the first thing of course is to fully extend the meter rule for 3 meters. The scale I will use is the actual astronomical units of each planet multiplied by 10 in terms of centimeters. So I start off by placing the Sun at the start of the rule in the 0 centimeter mark. This tennis ball will be the Sun, hopefully big enough for the integrity of the model. So far it doesn't look like much, just a rule with a tennis ball at one end. But everything changes when the first planet enters the model. Mercury. At 0.39 astronomical units, or 3.9 centimeters in our model from the Sun, it is the first and the smallest planet. Here it is represented by this yellow dye. Wow, we have placed our first planet, but see how much we have left to cover. So let's get going. Next is Venus. At 0.72 astronomical units, or 7.2 centimeters in our model from the Sun, it is the second planet from the Sun, and the hottest in our solar system. And thus, I have chosen to represent this planet by this red dye. You can see over here how close the two planets are relatively speaking, when we compare it to the rest of the meter rule. After Venus is its nice and lively sibling, Earth. At exactly 1 astronomical unit, Earth is the third planet from the Sun, and in our model, 10 centimeters away. This places the Earth on the habitable zone, where it is perfect for life to thrive in. So we've completed the model distances of the first 3 terrestrial planets, but we're still missing one more. Mars, the red planet. At 1.52 astronomical units from the Sun, or 15.2 centimeters in our model, it is the last terrestrial planet from the Sun. By looking at the model so far, we notice that all the terrestrial planets cover a distance of only 15 centimeters in our model, and still, there is almost 3 meters left. Let's see how the gas giants are distributed in our model. The first gas giant, Jupiter. At a massively increased distance from Mars, it places 5th on the line at 52 centimeters from the Sun, or in effect 5.2 astronomical units. You can see here that there is a massive space between Mars and Jupiter. This space is actually occupied by the asteroid belt. So now that we have started on the gas giants, let's look at the beautiful ringed planet. Saturn. At 9.52 astronomical units, or 95.2 centimeters in our model, it is the 6th planet from the Sun, and the second largest after Jupiter. You might be noticing why I used a purple dye for the planet. The reason is because I don't have any more yellow dyes left for the model. From this point, you can still see the Sun, but wait until we reach the ice giants. The first ice giant is Uranus. As the second last planet, it is 192 centimeters away from the Sun in our model, which corresponds to 19.2 astronomical units in real life. Uranus is the coldest planet, and this dye here represents almost exactly the same atmospheric color of real Uranus. Using this model, you can actually see visually that the distance to Saturn is basically doubled to reach Uranus. But how far is the last planet? At more than 30 astronomical units, 300 centimeters in our model, Neptune orbits the Sun as the last of the 8 planets. Its distance is so great you can barely see the Sun if you are in Neptune. It took Voyager 2 almost 12 years to reach the planet, despite the gravitational assist of the gas giants. So the model of the solar system is finished. And you can see here that the distance between the planets increases exponentially on average as you go away from the tennis ball or the sun. I find this concept of scaling truly amazing, as it helps astronomers to have a better idea of not only the solar system, but other complicated concepts such as atomic physics, where they don't scale down, but they scale up. But I've always been asking this to myself. How far away are the two Voyagers? Well, for that, we need to go out of my house and behind the backyard. So there we have our scale model, and at 123.62 astronomical units from the Sun, or 1,236.2 centimeters from the tennis ball in our model, Voyager 2 is receding at 15.4 kilometers per second. But where's Voyager 1? Well, let's see. At more than 148 astronomical units, 1,480 centimeters, Voyager 1 is receding at 17 kilometers per second. And thanks to these space missions, we now have a better understanding of almost all the planets and beyond. There you have it, the scale model of the entire solar system plus the Voyagers. We just traveled almost 150 astronomical units, but in reality it was just 15 meters. A recently hypothesized planet 9 is said to be around 600 astronomical units away. That is 60 meters away from the tennis ball in the golf club. Anyways, that's the topic for another video. Thanks for watching.